How did one company intercept the first moving target at sea, repurpose a spacecraft to chase a comet, and pioneer air-launched rockets, then vanish from aerospace history? It starts with Fairchild and a problem no Navy had solved. The Navy needed to strike enemy ships without flying patrol planes directly into heavy anti-aircraft fire. Born from the post-war Project Kingfisher and transferred to Fairchild in 1954, the AUM-N-2 Petrel solved this by serving as the military's first operational air-launched standoff anti-ship missile. Launched from P-2V Neptune patrol bombers, the Petrel combined a Fairchild J-44 turbojet and a solid fuel booster to carry an airdropped Mark 41 torpedo over 20 miles. Guided by semi-active radar homing, it plunged into the water near its target. Though retired by 1959, this design directly pioneered the standoff torpedo strike concepts later refined by the Harpoon missile. The Navy faced a parallel crisis, surviving high-speed jet attacks at close range. Under a March 1945 contract, Fairchild designed the SAM-N-2 Lark for point defense. Flight testing began in June 1946. Launched from the experimental ship USS Norton Sound, the missile originally used command guidance, where operators steered the weapon from shipboard consoles. The project culminated on January 13, 1950, when an automated variant completed the first successful interception of a moving aerial target. Although the Navy canceled the Lark for more advanced systems, it proved that guided shipborne defense could defeat the jet age. The Air Force turned from destruction to deception with the XSM-73 Goose, a long-range decoy designed to fool Soviet radar networks. Born from the 1954 MX-2223 studies and developed under the WS-123A program, this unmanned delta-wing vehicle used a lightweight, fiberglass resin-bonded composite structure. Powered by a Fairchild turbojet and controlled by a pre-programmed autopilot, the Goose took to the air in June 1957. But 15 flight tests revealed a fatal flaw. Despite its innovative materials, the Goose could not convincingly simulate a B-52 bomber's radar return, leading to the program's cancellation in December 1958. The Army required high-speed battlefield intelligence, steering Fairchild toward autonomous observation platforms. The SD-5 Osprey, which first flew in 1960, was designed to collect information instead of delivering a warhead. Catapulted into the air via a solid booster zero-length launch and sustained by a Pratt & Whitney J-60 turbojet, the drone relied on inertial navigation for autonomous flight. Its payload scanned for heat, terrain, and shapes using infrared side-looking radar and optical cameras before the craft returned by parachute. Ultimately, the Army canceled the program in November 1962 because it was too expensive to field. In 1982, NASA mission planners faced a choice: build an expensive new probe to study comets, or reuse what was already in space. They chose ingenuity over replacement. The spacecraft, launched in 1978 as the ISEE-3 Solar Wind Observatory, was retasked as the International Cometary Explorer. On December 24, 1982, flight controllers executed a precise delta-V burn, a calculated change in speed that bent the probe's orbit and sent it looping toward deep space. This trajectory design led to a historic flyby on March 30, 1985, when the vehicle completed the first-ever close encounter with a comet. The spacecraft later analyzed Temple 1, returning valuable scientific data. By squeezing new discoveries out of existing hardware, this quiet triumph proved that smart trajectory planning could give a retired asset a second life, establishing a precedent for flexible, low-cost space exploration. The challenge of reaching space shifted from government-funded giants to commercial access with Pegasus, a 3-stage, solid propellant rocket designed for small satellites. Instead of launching from a pad, a carrier aircraft transported the vehicle to an altitude of 12 kilometers before release. This air launch method bypassed the thickest layers of the atmosphere, reducing both structural mass and the high cost of ground-based infrastructure. On April 5, 1990, Pegasus achieved its first successful orbital insertion, proving that an aircraft could serve as a reliable first stage. For Fairchild, whose legacy in guided platforms paved the way for launch integration, this system bridged the gap between military missile development and commercial spaceflight, normalizing air launch as a highly efficient path to low Earth orbit. Fairchild's reach extended into orbit with the applications technology Satellite 6, or ATS-6. Operating in geostationary orbit, this civilian applications platform was built around a 10-meter deployable mesh antenna designed for direct broadcast and educational communications. During its experimental service in the 1970s, the satellite bypassed conventional ground stations to beam live educational television programming directly to remote classrooms and users in isolated regions like Alaska. By successfully unfurling this massive mesh structure in space, ATS-6 proved that large aperture deployment could turn experimental hardware into a practical public service. Instead of joining an active commercial fleet, the retired spacecraft was eventually preserved at the Smithsonian, leaving behind a legacy of large aperture engineering that helped shape the satellite communications networks we rely on today. As modern aerospace races into the future, Fairchild's fingerprints remain hidden in plain sight. What other forgotten innovations lie waiting in the archives to redefine our tomorrow?